Hello there guys, here is Max again, and today I will tell you all about the quenching process. At the left top I have drawn a steel bar which is being cooled by air. Air is of course just 300 kelvins room temperature. Because air is flowing around, heat will flow out of the system into the air, and therefore the temperature of our steel bar is dependent on time. Then I have a certain thickness of my steel bar, and you should also see that at the bottom of the bar no heat will flow out. This is perfectly isolated. Then our steel bar has a temperature starting at 1500 kelvins. The density of steel is 7800 kilograms per square meters. Cp is 0.49 kilojoules per kilogram Kelvin, and the lambda is 45 watts per meter per Kelvin. The first question was to calculate the heat diffusivity, and if you look this up you can see this formula. You can fill this in, just fill in the numbers you can see above. Watch out, since the heat capacity has been given in kilojoules, so you have to convert this, and then you will get a number which is 1.41 times minus 10 to the power minus 5 square meters per second. Then you have to calculate the Fourier's number for this cooling process. You know that Fourier's number can be calculated for heat by the heat diffusivity times the times divided by the thickness squared, but since this is a plate that is not cooled on both sides but at one side, this term changes into 2D squared. You have to really watch out for this, because for different geometries it could be that your Fourier's number can be differently defined. Now if I look at this equation and I want to calculate Fourier's number, I can see I have alpha, or A, the heat diffusivity, but I do not have the time, and I also do not have the thickness. So this is not the right way to do this. How can you do this then? By using the graphs given in the exercise, where you can calculate or you can read out Fourier's number if you have m, and you have to use m that was defined at the maximum temperature, since we were interested at the temperature of the steel bar at the maximum of 500 kelvins. So no point in the steel bar was allowed to be hotter than 500 kelvins. You can look up this formula as well, where T1 is defined as the boundary conditions, which was the temperature of air, which is 300 Kelvin. Tc is the hottest temperature, which was 500 Kelvin, since this was allowed. And T0 was the initial condition at T is 0, time is 0, and then the steel bar was 1500 kelvins. If you fill this in, you get m is 0.167. Look in the graph at the plate configuration, and then you will see that Fourier's number is around 0.225. This was how you had to calculate it. Now they wanted to know how long it would take to reach this temperature for a plate with a certain thickness. Then I can use the formula we've just seen. Since now I do have a thickness, I have the A and F here number, only not the time. So I can rewrite this for time, which is then VA's number times thickness squared divided by heat diffusivity. Fill in all your numbers and you will see it takes 151 seconds. Please, if you have still any questions, feel free to post something on the forum. If not, continue with your next exercise. See you next time.